So welcome back to Introduction to Machine Learning, or Machine Learning 1. And it appears that the microphone is indeed working now. So I can actually use the recording from the computer. And yeah, I think everyone should hear me online fine. So I guess what just happened is we had a midterm. I actually got an email from the Scantron people that the midterms are now marked. I haven't looked at the marks, but they should be released tonight, I guess. Well, I looked at very briefly. It looks like the average is above 50%. That's all I can say. But I think it's higher. I don't know. We'll see. It's definitely above 50. Like there was. Look at. Okay. I mean, that shouldn't scare you. That's good. So, yeah, I'll release the marks tonight, and I'll also release the solutions. So you can I'll release the midterm and the solutions of the midterm and what you answered, so you can just check yourself what happened. And then if you have questions about that, you just go to the TA's office hours and discuss with them. Okay, so that's how that works. And now we get back into learning. And let's remember where we were. So as you've seen a couple times now, this empirical risk minimization thing is very important. And yeah, we don't talk about too many theoretical details, but roughly speaking, there are results that show things like, why are we using empirical risk minimization? There's surely other ways we could do all this. And there are results that are really saying things like, this is really the best and kind of the only algorithm you need. In the sense that you can show theoretically, if you have a problem and there's some minimal amount of samples that you will need to solve the problem, well then ERM will actually solve it in that many samples. So it will require data sets of that size, which is really nice. So just to point out, there's good reasons to be just studying kind of this thing more or less. Okay, and so how did this work? Well, it worked, as I've said many times, is you want to minimize the expected loss or the risk. And the thing to keep in the back of your mind is that hopefully you were convinced that this risk is just a single number. Well, I mean, this is true. It is just a single number that describes somehow the quality of a predictor, right? So that's this L guy here. So you plug in an F. This gives you a single number. And you can plug in any predictor in there, and that gives you a different number for every predictor. Maybe some of them are the same number. The thing that hopefully was motivated is that this number somehow properly describes our understanding that this is the quality of that predictor. So the smaller the number, the better the quality. It means it errors on less things. It has a lower loss. And so hopefully if you're convinced that this number actually does accurately describe what we want, which is the quality of the predictor, how much error it makes, well then all we're left with is just trying to minimize this number over all possible functions we could plug in. And since we don't have access to that, we estimate that number with this L hat. So we get the empirical risk, an estimate of it with data, and then we just minimize this estimate. And then the story goes as follows. If you have enough data, then your estimate of the risk is good. And if you have a good estimate of the risk, of course, minimizing something that's extremely close to the thing you really want to minimize is a good choice. And so and then we talked about last class, we kind of wrapped up our first actual algorithm that you can implement on an actual computer, which indeed does somehow search over a set of functions, a function class, and minimizes this estimate. And so how did that algorithm look? So let's look at that piece of that algorithm pseudocode. That would have been somewhere. I guess it was in this lecture. Here's our algorithm. Let's just jump right into it. Right. So this is a definition of the learner A. And remember, the learner has to take in a data set. And surely it does. So this is your input. You got your data set. It has n data points. Then it does, so let's just look at what happens, and we'll map it back to URM in a second. So it does some manipulation with the data, calculates a matrix, calculates a vector using the data, right? These are just operations on the data, the features and the labels and so on. Then does some other operation, takes an inverse, multiplies the matrix by a vector, gets another vector, and then says, okay, this process, which seems very odd if you don't know the background of how we got here, is then going to output a predictor in the way that we take the dot product with a corresponding feature x. So basically, we'll output a new function called this is our predictor function. This is the output of our learner. And the way the function works is for any new feature x, it will output that x times w. And maybe, okay, let me write this in a slightly different way just to make this absolutely clear what's going on. So what's really happening, right, is we're not like this notation can be a little bit misleading sometimes. It's not quite like, you know, like a function, when you plug in a number, that's just a number. That's a little bit weird. So what I mean to say is that what is actually being returned, right? We really need to return a function. So just to be a little bit more precise, you would actually write this something like, and in Python, what would happen is you would really return a function. Like that would be you would return like an actual, you would define like a function, and then you would, you know, actually return that function at the end. Okay, so what you would do is you would pay like, I'm going to return f hat. That's actually a function, right? Okay, a function from x to y, that's f hat. And then you would say where my f hat is defined as follows. For any input x, it does the following behavior. So where f hat is this, and this would be for all x coming from calligraphic x. This is just to make it very clear that you are really returning a function, which is a map from any input from an x to an output y, a label y. And it's defined through this definition, which is based on the w hat. Okay. And indeed, it takes in data, does some operations, and produces something like this. And the reason we claim this was a good idea, or this worked, or whatever, it did what we were trying, it was implementing ERM, is because the story was like, what did we do? Well, we, let's just recap. So we looked at our problem, what was ERM trying to do? And ERM was just trying to output f hat that was the function in our function class that made the empirical risk the smallest, right? And then it turned out that we're going to make some assumptions of things, like we're going to make some choices. And one of those choices, well, let's pick a function class. The algorithm we saw was the case where the function class was a set of linear functions. That was this class. It was where every single function looked of this form, and therefore it was represented by a single, there's one parameter that describes every function. Every function has a parameter that's described by. Okay, and then it turned out that minimizing this object was the same as just finding the parameter that makes like this quantity, this empirical risk, the smallest, where you actually plug in f as a linear function. So that's just below here. So you want to find the minimum parameter w that makes, this is just plugging in the definition of the empirical risk for a linear predictor. And so then we saw that if we looked at this object, this looked very much like this optimization setting stuff we learned before, which is now you're minimizing over some multivariate parameter vector. It's just a number in RD, it's just a vector. And you just have some function here of that d-dimensional vector. It's complicated looking, but yeah, you have a function. And then we also said, you know, if this thing was convex, then we're basically done, because then we just do the same things we know. We just take the gradient, set it to 0, and we're good to go, and we know that will be the minimum. And it turns out that because of our choice of this function being a linear function, and because of our choice of L being the squared loss, which is this thing here, then indeed, the function we're minimizing, this thing, the empirical risk for a parameter W, is going to be convex. And then doing our process that we know will give us the minimum, taking the derivative, setting it to 0, will minimize this function. And that's all that was left to do. So then it turns out that if you do that process, which is take the derivative in every single dimension, set it to 0, and solve for the corresponding parameters W, you end up with that system of equations, which we got to at the end here, which is it turns out that the solution, that the parameter that minimizes that thing we just saw above, has this form where A inverse, well, where A is this thing and B is this thing. And that's just some things based on data. They're just solving a system of equations. And yeah, that's it. And maybe one more thing to say is that you should think of this algorithm as kind of like giving you the solution maybe in like kind of in one shot, in the sense that like you just take the data, you just plug it into some like equation, and it just outputs the correct answer. And people will call something like this is like your closed, it's like a closed form solution. It's just you plug in data, you get a thing, and you're kind of done. And like visually, I guess we saw this kind of near the end of that supervised learning lecture, is what you would get is exactly the following, which is if you had these black points, which were data, right? Then the solution would output a line that looks like this, that somehow best fits the data in the sense that the squared distance from all of these points, which was that squared loss, is minimized. And so it just one shot outputs this line, okay? And this is going to be in contrast to what we're going to work on today for various reasons. We'll see why we would want to do this. This is different than a solution that kind of like iteratively finds this kind of like line. So like just to give you an idea, like you could imagine instead of just taking the data and immediately outputting the line, you could like make a guess. Oh, maybe it's this line. And then you're like, oh, that's a terrible choice. Let me improve that a little bit, and I can iterate and pick this line next, and then pick this line, and so on. And you're going to do a bunch of these iterations until you kind of converge to the best possible line. And there's going to be various advantages to doing that. And that's roughly, I mean, that's exactly actually what we're going to do today for optimization. Okay, so yeah, so let's get into today's class. So today's class is going to study a different way of solving this like optimization problem. We're not going to just take the derivative and set it to 0, right? If you take the derivative, set it to 0, solve that system of equations, you just have an equation that gives you the minimum right away. And the question might be, why not do this all the time? And there's going to be two kind of reasons. The first very obvious one is let's just try to do it again for the following function. Let's just do it for fun. So we have a function here, right? Visually, you can see it's convex. We're going to also confirm that it's convex by taking the second derivative and setting it to 0. And then after we've done that, we're going to use the first derivative, set it to 0. Sorry. We're going to confirm it's convex by taking the second derivative and noting that it's non-negative. And then, since it's a convex, we'll take the first derivative, set it to 0, and try to solve for w. Okay, so that should be easy enough. So here's our example. The function is as we saw there, right? It's g of w equal to w squared plus e of w. Now let's take the first derivative. That's 2w plus e to the power w. Let's take the second derivative. That's just 2 plus e to the power of w. Well, e to the power of anything is positive, and 2 is positive. So this is definitely greater than or equal to 0. And so this tells us, first observation is this is indeed convex, as our eyeball has confirmed earlier. Now, let's try to solve for w star. So that would mean setting the derivative to 0, right? So this is 2w plus e to the w, and we set it to 0. Okay, and now it turns out that if you try to like solve for w, you run into a lot of problems in the sense that you can't write out an equation for what w should be using like what are called kind of elementary functions. So things like polynomials or cosines or exponentials or inverse functions and so on. So there's no what is called, this is like if you can't do this, then what people will say is that there is no closed form solution. So there's no closed form solution for w star. And w star will be the w that makes this equal to 0. And so that's kind of the first reason why setting the derivative to 0 and solving for w is not going to be a great idea. Yeah. Yeah, but then you're going to end up with like some log of something else. And I mean, let's try it. So we have let's maybe move it to the other side. We have EW equals minus 2W. And then you can take the log of both sides. So this will give you w equals to log of -2 over w, which is the same as like 1 over 2w. Well, let's just write it. And now you need to solve for w. You need w on one side, right? I just need like w equals something. And I still can't rearrange to, like, I haven't really gotten anywhere here. Sure, we can do that too. So this, the right-hand side is equal to log of -2 plus log of w. And then, okay, I can try to move the log of w to like the left-hand side, but somehow I still am like, okay, so let's do that. So this will imply that I have log of -2 equal to w minus log of w. But I still don't have an equation where I just have w equals something. I have w minus log of w equals something. Anyways, you can keep trying to like play around with this various ways, and you will not have luck unless I made a mistake. But even if I did make a mistake, which I don't think I did, there is indeed like equations where you just can't solve. There's no like closed form solution for that expression w that can be written as in terms of like logs or exponentials or polynomials or so on. Okay, so that's kind of the first motivation for why this setting the derivative equal to 0 and solving is not always going to work for us. Okay, and the other reason that this is not always going to be a good idea is because, as you saw in general for like the multi-dimensional case, when you do this, you get this giant system of equations. And even in the nice setting where things are like these, like a linear system of equations, as we saw, you're going to end up with like this matrix inverse, right? Which was like that A inverse. We saw that you had like A inverse before. And calculating an inverse is quite expensive computationally. Okay, it's going to be approximately, it's going to take like cubic number of operations in the dimension of the matrix. So it would take approximately, so like calculating this, that's not how you spell calculating. So calculating A inverse approximately takes d cubed operations on a computer. Which you should think of, which is a lot, okay? So we're going to want to bring this down somehow to have less operations. Because if D is like very high dimensional, so like in, for instance, the neural networks of today, D can be of the size 1 trillion. So if you take 1 trillion cubed, good luck taking its inverse or doing that operation. So we're going to want to bring that down. We're going to bring it down to something like D squared, which is quite a bit of a improvement. Okay, so hopefully this motivates not just setting, or why we are not done by just setting the derivative to 0 and solving all the time. Okay, and so we're going to get into our first other method, which is going to be like a variant of gradient descent. We're going to call it second order gradient descent. For reasons you will see why it's called second order, but people actually, I think, well, not that I think, it's actually quite commonly given the name Newton's method. And if you do any sort of like numerical analysis courses and stuff, you'll always hear about this Newton's method stuff. And we're going to see how it works today from kind of two different perspectives. And so to understand what, like, let's just intuitively build up to what's going to happen here. How are we going to do this? Well, like, we want some sort of, I don't know, I want to find this minimum somehow. And like, okay, I'll just tell you some like high level idea of what an approach might look like. Well, like one approach is like, okay, let's just like somehow, I don't know, let's approximate this function, right? So we have like a function that, like, since it's convex, you know, we know it looks kind of like a quadratic function or like something like this. It should, so why don't we approximate it with a function that we actually know how to just set the derivative to 0, right? So we saw that like for like a parabola, a quadratic function, we can indeed take its derivative, set it to 0. There is a quadratic formula, and we can just find it. So like, why not just approximate this by a quadratic, find the minimum? That's pretty close, you know. And then, guess what? It turns out that, you know, if you find that minimum, it's pretty close. And then you can iterate, because then you can take that point, be like, oh, why don't I now, what's going to happen is the approximation of the function is going to be based on like at some location. So you can then approximate it at like the point you just found, and that's going to be a better approximation, and you're just going to keep iterating this process. So that's going to be kind of the rough idea. So let's just start with this first idea. Let's just try approximating this with some function which we know how to find the actual minimum of. Okay, and I alluded to why don't we use a quadratic function, but like more generally, why limit ourselves to quadratics? And there's kind of a good reason. So here's an interesting result that I don't remember when this was found in math. I think it was at least 100 years ago though. But it turns out that if you have some function g of w, so if g of w is a, let's say, at least a degree 5 polynomial, right? So this means it has at least a term in there that looks like, you know, like x to the 5 or higher. Well, then there does not exist a closed form solution. Wow, a closed form solution for g of w equal to 0. So this is pretty fascinating, first of all, just from like a mathematical perspective. So in like high school and later on, you probably learned that if you have a, you know, if you have a quadratic function, which means that it's a polynomial of degree 2 or less, you have something called a quadratic formula, which is just an equation that gives you the points at which it's equal to 0. And then you can keep extending this, right? It's like, then you have a cubic function, right? Polynomial of degree 3, and then there is a cubic formula. It's like half a page long. Then if it's to the power of 4, like a polynomial of degree 4, there is indeed like, what is it called? I guess they call it a quartic function or something like this. And that one's like 2 pages long of the equation, but you can still, you just plug in the numbers and you calculate it. And then it happens that you can show that if it's a polynomial of degree 5 or higher, there just exists no expression to find the roots or the values where it's equal to 0 at all. And this was pretty weird and fascinating. And yeah, people in math like this a lot, and has a lot of other deeper stories about it. Anyways, this is an interesting fact. So clearly, what is this telling us? What's this telling us is that we're probably not going to want to pick a polynomial that's very complicated. Okay? And so then we kind of have a choice. We have a choice of whether we pick a quadratic, a cubic. Well, a cubic's kind of not a great choice probably too, because like it'll look something like this. So then we have like a quartic or a quadratic. And we just take the easy way out and pick a quadratic because it's simple enough, and the quadratic formula is nice and things like this. So yeah, so let's go ahead and do that. So this is going to be our approach. So our approach is going to be to approximate g of w with a quadratic function. So yeah, a second order polynomial, which is a quadratic. Okay, and so you may have learned as well, or remember in calculus, that the classic way of approximating a function with a polynomial is using the Taylor expansion or the Taylor series. And so a Taylor series, you can do this in general for any, like you can approximate it up to any order polynomial, and we're just going to cut it off to like the second order approximation. Okay, So yeah, we're gonna, with the second order polynomial, using the Taylor's approximation. Okay, and so that's an equation that hopefully you're familiar with and heard of before. And so what does that look like? That's going to look like we have g of w, and now we want to get an approximation of it. And that approximation is going to be called g of also w. But the way it's going to work is that you have to pick a point at which you approximate at. And at that point, it's going to be a perfect approximation because it's going to be exactly equal to the other function at that point. And then everywhere else, it's going to start being a weaker approximation. And so that point which we pick to approximate at is going to be called w0. And this superscript 0, you'll see there's a good reason we use 0 and so on. But that's just your initial point. Kind of have no idea where to pick for that, but that's where you're going to approximate at. And at that point, you're going to have a good approximation. Farther out, it's not going to be as good. And so, yeah, the equation for that is as follows. You take the original function, g, and you plug in g of w naught. Okay, so at this point, they're clearly equal. If w was w naught, then these are clearly equal. And then you have other terms. So then there's the first derivative term. Yeah, and then you have a second derivative term. Okay. So this is our approximation. And yeah, you can see if w equals w naught, then w would, right, okay, let's, so this is a function of w. This is also a function of w. In what way? Well, this is a constant. This is also a constant. This is also a constant. So the w's only appear here. And if w equals to w naught, then this is 0, and you just get g of w naught. So it's a perfect approximation at w naught. And then everywhere else, it ends up being a little bit weaker. Okay. And I guess I have a picture of this. So this is a picture of approximating the function we've seen so far. There's going to be a lot of pictures now. This is why there's notes that I shared online. It's just a bunch of plots that we're going to like slowly build up the story of what's happening here. Yeah, so we have this picture, and this is our approximation using Taylor's approximation at a w naught that I've completely chosen arbitrarily because you have no idea where the minimum is in general. I mean, here, yeah, visually I can see where it is, roughly speaking, but in general, you're not going to know where it is in multidimensional cases. So I just pick some arbitrary w naught, like w1. You can see it's a very good approximation here, right? And then as you get further out, it's not doing so good. Okay. Yeah, and so this orange guy is like g of w naught, where w naught equals to 1. So just chose it arbitrarily. So now what's going to happen is we're going to want to find this minimum. Roughly speaking, we're going to find the minimum of the approximation, which is here. And then we're going to take the point of the original function at which this happens. Well, we're just going to take the point at which this happens, which is like the w value. And we're going to say, oh, that's sort of close to this. And we've got like an approximation to the minimum now. So let's just do that. How does that look? What does the equation look like? There's going to be a closed form solution, and we're going to make use of this closed form solution quite often. So our goal is going to be like to minimize g of w naught of w, right? And the way that's going to work is we're going to take its derivative and set it to 0. Or maybe I should write that our goal is to find, so our goal is find the argmin w in some domain which we have not talked about yet of this function. So the way that's going to work is we're going to take the derivative of this function. And just maybe I should remind you again, remember this thing is our quadratic approximation, it's the orange function above, right? So let's take the derivative. Let me remind you, what is this equation? It's this. So yeah, just so you can see visually, we're going to take the derivative of this guy. Let's do that. The derivative of the first term, that's just a constant, so there's nothing there. Derivative of the second term, well, that's just this constant times double. So the derivative of that would just be the constant. So you get g prime of w naught. And then the derivative of this, oh, there's a mistake in this. I completely forgot one thing. Clearly, this term should be squared. This is the quadratic part. This is the squared part of the approximation. And so here you also have the squared part. And that's also why you have a squared looking function. Otherwise, you just had two linear things. Would have made no sense. Okay. So the derivative of this guy, you do the chain rule. The 2 outside, right? This 2 comes outside, cancels with this 2. So you get this term left. And then you take the derivative of the inside, which would just be 1. So you end up with plus g double prime w naught 2 canceled, and then you get the w. Oh. Yeah. So you get this term left over. Okay. And so we want to set that equal to 0. And then we are going to want to solve this. And so let's do so. We want to solve for w, right? So that's going to look like g double prime of w naught times w is equal to g double prime of w naught times w naught minus g prime of w naught. Right? And keep in mind, these are the derivatives of the original g function, right? Second derivatives and then first derivative. Okay, and all that's left now is to just, divide both sides by the second derivative and end up with the following, which is w star, which is what we were trying to solve for, is equal to just w naught minus, oh, we're missing this. Oh, no, we're not. G prime of w naught divided by g double prime. Okay, this turns out to be the solution for w star here. Okay, so let's try it for our function that we had above. So we had this function here. Visually, this is the minimum that w star is. This is w star. And for the, I guess you can already see, but the following, we're going to use the following notation, which is the solution to this. We're going to say w1 here equals to w star for now. And you'll see why we do this notation. So when you use w0, you're going to get that w1 is the solution, and then we're going to keep doing this iteratively. So yeah. So visually here, this w1 is the same as the w star we just solved for. It's just this minimum point here, right? Well, the line, this w1 is this point here. The value will be if you plug that in to the actual quadratic, but all we care about is the actual w value. So it would be this point here. Okay, so let's solve for w1, just like in this equation. And let's see that we indeed do get what should be 0, right? It should be the value 0. All right, so how is that going to look like? Well, we chose, yeah, I guess I'll do it in orange. So we chose w0 as we saw to be 1, right? And then we're going to need both of these things, which is the first derivative and the second derivative. And we already calculated these, so let's just take them and copy them over. So I already have these. So now I can calculate the first derivative with w naught plugged in. right? Because I'm gonna, once again, what am I trying to do? I'm just trying to evaluate this formula, which all that means is I need to calculate G prime, G double prime, plug in W naught, which is the number 1, and see what I get. And so I plug in 1, because that's what W naught is. And I see what I get is 2 times 1, and then e to the power of 1, which is just e. So 2 plus e. And the second derivative at 1 is equal to 2 plus e. And then from the above formula, I know that W1 is equal to W0, which is 1, minus the first derivative evaluated at 1, which is 2 plus e, over the second derivative evaluated 1, which is 2 plus e. And I get the value of 0. Okay, and so this does indeed check out with what we saw here, which is the minimum is at 0. So just double check that we've done everything kind of correctly. Okay. Hopefully that makes sense so far. And there's a question. Yeah, and the question is, why is this method better than doing a binary search to find the minimum? And roughly, so like what the binary search would be something like, I don't know, you pick a point, and I guess you need some interval, which you're looking in, which maybe is the whole range, and then you like pick some point, and then you see what the value is, and then if it's smaller than at the endpoints, well, okay, then you pick some other point, and then if it got bigger, then maybe you go the other way, you go lower, and so on and so on. That's a good question. I don't know. I don't have a good answer, actually. I don't have a good answer. Well, my answer is going to be that I'll think about it more, and if I remember, get back to you next time. I think it might have something to do with like, okay, yeah, I don't know. I'm not sure. But I'm sure this is a better idea. Like roughly speaking, it's going to be something like this. Well, we're going to see another interpretation of this in a second. Maybe I'll mention it then when we get there. But roughly speaking, this, like, you can see that we started at this point, and we somehow moved all the way here, which was like a pretty good step. You know, like we're going to talk about this being like a step in the direction of the minimum in a moment. And it turns out that like the kind of choice of how far you should move down is actually going to be exactly governed by like this second derivative here, which we'll see in a moment. And that somehow is more accurate of how far you should move along than just randomly guessing in halves. But that's about as best as the answer I got so far. Okay, so yeah. Okay, so anyways, let's continue with the story. So we had yeah, so we started at, you know, we could have just started with guessing some minimum, which is like we guessed some W naught. Well, this was some value, and it's like, I don't know, like maybe I guessed really poorly, maybe not. The thing to notice is that now we've gotten a better estimate of the minimum. It's over here, but it's not quite the minimum. And so like, can we do something else? Like, can we improve on it? And the story is going to be like, well, what we have now is a kind of like a better starting point to then make another approximation and repeat the process again, right? So if we could approximate the original function as close as possible to the minimum, so if this W naught was as close as possible to the minimum, then this orange function would have been an even better approximation, and its minimum would have been even closer to the true minimum. And so what's going to happen is this is going to give us this iterative process that says, well, guess somewhere, then find the minimizer, use that minimizer as your next guess, and then approximate from there, and then get another minimizer from that, and repeat that process over and over. And that turns out to be very efficient. So visually, that looks like this. So we take this as our new starting point, W1. We're going to do another Taylor's approximation. From there, we get this green function. And then we're going to find its minimizer, which is going to be somewhere around here. And visually, that's going to be like this purple thing here. And you can see this line, this purple line, is almost exactly at the black line. And so this W2, which is over here, is going to be extremely close to that. And so we're going to do that calculation one more time, just to get a feel for what happened. So yeah, I mean, I'm not even going to write out the first step of the calculation, but you can do this calculation again. And you can do this whole process as well, which you can take the derivative, set it to 0, but now instead of W0, you have W1, right? And you're going to get an expression like this, but with W0 replaced with W1 here. And then you're going to get that the new W star is just equal to the same thing, but with W1s placed in here, right? That's the only thing that's going to change. The point at which you're approximating at is now replaced from W0 to W1. So what I mean by that is that this new point, the purple point, is now going to be the following value. It's going to be exactly equal to this expression, which is W2 now is going to look like the previous expression, but with W0 replaced with W1. So you get W1 minus G prime at W1 over G double prime at W1. So all we've done is we've repeated the exact same thing, but now for a different function, which is the function that uses W1. And that's exactly this green function. The green function is a perfect approximation at W1, and everywhere else it gets a little bit weaker. And so if we plug in the values of W1, which we saw before, which are 0, right? So I mean, I guess we can do it. So you would get W1, we saw above was 0, so you get 0 minus G prime at 0. Right, it's going to be G prime at 0. That's going to be 0 plus e to the 0. That's 1. And then you're going to get here, which is 2 plus e to the 0, which is 1. So you're going to get 1 over 3, right? Minus 1 over 3. That's W2. And as you can see visually, that looks like 1 over 3. So that's just, yeah, you do that calculation. And as you can imagine, we're still not quite at the minimum. So we can do this again, and again, and again. And you get this general expression, right? So in general, you get the following story. So at iteration t, you use the guess you have at time step t. And then you get your next estimate, which is w of t plus 1. Let me just make this a little bigger. This is t plus 1 is equal to that formula we saw, which is w, your guess at time step t, wt, which you had calculated, minus g prime at wt over g double prime of wt. And yeah. And so this holds for all t that are an element of 0 up to whatever you want. I mean, sure, it's a natural number. Okay, and W0 is your initial guess for all, and W0 is your initial guess. And so you can keep iterating this process, and the story is that Wt plus 1, and we're just going to say this like roughly speaking, approaches W star as t goes to infinity. So as you do this iteration enough times, infinitely many times you'll get to the minimum. But for any finite t, you're never guaranteed that you've made it to the minimum. But you will be very, very close. So in practice, usually you don't care about getting the perfect minimum. You're okay with like being like up to some error close. So you'll just do this process like, I don't know, 5, 10, 20 times. And then you can just see, oh, is my error between time steps shrinking? Like, is it tiny now? which means that I'm basically there, and then you can just stop. Or you can just preset t to like 100, and you'll probably be okay in most cases. Okay. So that's Newton's method, and it works extremely well, actually. And so you can use it sometimes, but often we will not use this in machine learning because it's still going to be too expensive. And in particular, we're going to use something else called, and people will omit this, but we're going to call it first order. But really, this is what people mean by when they say gradient descent. So first order gradient descent. And from now on, when we say gradient descent, and so far you've seen nothing about gradients and you've seen nothing about descending. And so the second order gradient descent might be very confusing why it was called second order. Well, why you saw the word gradient descent at all. Where was the gradients and descending, but we'll see that now. Okay, so first order gradient descent. That's kind of going to be the story of the rest of this lecture and the next lecture and the following lecture, and how all of like neural networks and everything is trained is kind of through this method of gradient descent. Okay, so how does this work? And the motivation is something like, you would like to do Newton's method. I mean, really, you would like to do it even with you'd like to do it even with a quadratic polynomial, but we didn't do that operation. And that's because we did it in the 1D case. And in the 1D case, it's fine. Like calculating the first derivative is not too bad. In the multi-dimensional case, right, the first derivative would be like you take the derivative of every single dimension, that's a gradient. That's maybe not so bad either. You just need to take it for every dimension. The second derivative, though, gets messy, because if you remember, if you have a function, g, and then you take its second derivative, then you take it with respect to like maybe w1, and then you take it with respect to w2. I think this is how people write it. I don't even remember. But you have to take it, like there's every possible combination of this index and this index. And so I could write it as like, in general, this would be like an I, and this would be like a j. And so if there's d dimensions here and d dimensions here, you end up with d squared, basically gradient calculations, or second derivative calculations. Sorry, second partial derivatives. And so that's going to be the like rough idea of what a second derivative looks like in multi-dimensional case, and they call this a Hessian. So it would be a matrix. It would be a d by d matrix, which has every possible combination of these second derivatives. And so the story is that calculating the second derivative which is really called the Hessian. I think that's how you spell it. Is computationally expensive in higher dimensions. Okay, so we're going to kind of, and that was, in the one-dimensional case, that was that second derivative in the denominator. And we're going to want to try to kind of avoid calculating that, that term. Yeah. Oh, two S's. Yeah, that looks more right. Thank you. Okay, so yeah, that's the story there. So calculating this Hessian is computationally expensive in higher dimensions. So what we're going to do is we're going to just remove that second derivative term kind of entirely and just plug in a constant. So yeah, let's look at this equation we have up here. Let's take it. And let's remove this term entirely. We don't want that there. And we're just going to put a constant there, which we're going to call eta. And we're going to allow it to change with the time steps. Okay. So instead of having this giant matrix, it's now going to be approximated by just a single number. And we're just going to do this. There's all sorts of methods in between, which then, because that matrix has like a bunch of entries, right? It has d squared entries, which is an entry at every point. People will then approximate it by something kind of in the middle of these two cases, which is they'll approximate it by a diagonal matrix. And so then you'll have just D entries, which is just an entry on every diagonal, and you forget about the cross terms of the matrix. That's a better approximation than this. And that will work better, but it will be more expensive. And there's all sorts of unbelievable amounts of research that goes into picking how you should do all this stuff. Okay. But for now, we're just going to study this case and for the rest of this course. And so this term, for reasons we'll see very soon, so eta of t is what is called the step size or the learning rate. And we'll see how this is to do with the idea of learning and the rate at which you're learning and so on very soon. Okay. And so we're going to still study the 1D case for now, just to see how this relates to the second derivative and if we don't use the second derivative. And like, ideally, right, let's just see how this maps to the second order gradient descent thing and how now we'll see the relationship. Like, ideally, if we somehow knew the second derivative, so if we knew g double prime of wt, then really the best choice is just to set eta to what we saw before, which is 1 over that. Yeah. So we should set, of course, we're not going to actually calculate it, but let's just, but this is like a property you should know that like this is kind of like your best choice. Which is you would like to set it to that. Okay. And so now continuing with the plotting example, we're going to interpret how to think of this operation in a different way, in what is actually kind of like, well, what this meaning of gradient descent means. Like where are you descending and with what gradient and whatnot. So first observation is that the gradient in one dimension is the same as the first derivative, right? And then in higher dimensions, the gradient is going to be this vector of each of the partial derivatives. So at least the gradient part's sort of solved right now because we're just working in the one-dimensional case. So for us, gradients are first derivatives. So here's a gradient. Here's a first derivative. Okay? And now I'm going to explain to you what it means to descend according to the gradient. And we're going to do this through a picture again. Okay. So you have your original function. And you might remember in calculus that there is this interpretation. Well, I mean, the gradient, or the first derivative, is the rate of change of your function at the particular point at which you calculate the first derivative at, right? So you take a first derivative. So you would get g prime, and then you plug in w naught, let's say, which is this point here, into g prime, and you would get the rate of change of the function at this point. So for like a quadratic, okay, well, whatever this function is, this guy here, we got the rate of change. It turned out to be 2 plus e, if you remember. So that was the rate of change. You can then draw a line, which is called like the tangent line, which goes through that point and has the same slope as that rate of change. And that's what we've drawn here. Okay. And so this is like somehow gives you a representation of what the derivative or the gradient looks like when evaluated at a particular point. It will tell you the rate of change of that function, right, at that point. Okay. So that's all well and good. Let's see, like, if this kind of thing gives us some information about which direction, right? This is what it's going to tell us. It's going to tell us which direction we should go at to reach the minimum. Okay, so the derivative here is positive, right? It's increasing. So let's just write that. So this is like a positive gradient. And let's just draw some other ones. I mean, like, you can draw it here. Another kind of tangent line. That's the rate of change at this point here. And that's also positive. And the general trend, you're going to see that anything right of the minimum for a convex function will have a positive slope. And I mean, we've already seen this in various ways. The definition of a convex function is that the second derivative is greater than 0, right? Which means that the rate of change of the rate of change is increasing, which would mean that if the rate of change here is 0, then afterwards, if the rate of change is increasing, it must always be positive, another interpretation. And conversely, anything on the left-hand side, if you take any one of these, okay, that's not a good line, any one of these guys, then they have negative gradients. Okay, and this is the important observation, that the gradient, and this will hold in higher dimensions, it'll tell you in each one of the dimensions, the partial derivatives will tell you that, well, they're going to be either positive or negative, and it's going to turn out that if you're to the right, in terms of the x-axis, or the w-axis here, then the gradients will be positive, or the partial derivatives will be positive. Maybe I should say, I should really write here, derivative. So negative derivative, and in the higher dimensional case, these will be partial derivatives. And this is positive derivative. Okay, and the observation, yeah, once again, is to the right, it's positive, to the left, it's negative. And the reason I'm pointing this out is somehow we're going to want to make use of this information to inform us, and in what direction we should shift our initial guess, right? This is like what we're trying to do. We have our guess W naught, and we look, and it's some, I mean, I don't know, I get a number. I can evaluate my function, but what do I do from there? Do I go left or right, for instance? Well, it turns out that if I just calculate in the one-dimensional case the derivative, I know that if I'm to the right of the minimum, it's going to be positive. And so what's going to happen? You're going to want to go in the negative sign direction of the corresponding derivative. And so going up according to the derivative will be called ascending according to the gradient. And therefore going into the negative is going to be descending. So we're going to go in the negative derivative direction, the negative gradient direction. Okay, so that's where the name this negative or this gradient descent business comes from. And yeah, and so that's all I have to say about it. So what we could think about in the previous case, so let's maybe just look at the example we had before. We had this example where W1 was equal to W naught, and this equation now becomes way more interpretable, right? Which is, yeah, so minus W naught, and then it was, I'll write it like this, G prime of W naught multiplied by the optimal kind of step size, which is G double prime of W naught. Okay, now we can kind of interpret what happened here. Our next point, or like our next value of the function that we're going to get to are kind of this W1 point, which is where we're going to somehow think about we're starting at W0, and we're going to take a step to W1. Should be thought about in this equation as you start at W1, you then look at the gradient at, sorry, you start at W0, you then look at the gradient, the derivative at W0, which is this thing here, and you look at what's the sign of it. If it's a positive sign, then you want to go in the negative direction. If it's a negative sign, then you're going to want to go in the positive direction. So the negative here, applied on this, will give you the sign of which direction you want to go. Okay, so that will give you basically the descent direction relative to the gradient. And then the last thing is, how much of a step do you want to make in that corresponding direction? And you can see the step size is going to be dependent on where you are. So if you're like far away over here, you're going to want to make a big step. But if you are like, I don't know, over here, you're going to want to make a very small step. And somehow it turns out that 1 over the second derivative governs the size of the step you should be making. And so this is kind of like the optimal step size, but we once again just approximate that with a number. So this was the ideal case, but in general, or like what we're going to be doing is plugging in a to t. And so that should be thought of. Now, hopefully the word step size makes sense. And we're going to see how it also makes sense to call it a learning rate, because we'll see that we're learning the minimum in an iterative at some rate. And this tells us the rate. We're kind of learning the minimum. And of course, this is 0. Okay, so this equation will really give us W1. And in the case we saw above, so yeah, in this picture, this quantity really was this 1 over the second derivative. So if you use 1 over the second derivative with W naught equal to 1, you do get what we see in the picture here, which is this point here is 0. We've already done this calculation. Now what we're going to do next is we're going to like kind of study what happens if we pick learning rates that are not the correct kind of learning rates. Yeah. Okay, so this was just the same example as we saw before, except now we're viewing the calculation we saw, right? Which was, so you started, so this is still just repeating what we saw with the optimal step size. And in particular, let me just write it. So now you're going to see that this purple thing, this W2, is calculated as W1, which we saw above was 0, minus the optimal step size, which was G double prime at W1. Right, and this quantity here, this is like equal to the step size, G prime. And this just gives us another interpretation of what happened before. So we started at W0. We calculated the gradient, this thing here. We then took a step size that brought us to this point W1, which is of this size. We then took this point W1. We then calculated this gradient at W1, which is actually this exact term. And then we took another step size of size 1 over the second derivative. And we ended up over here, which was W2, which was now quite a lot closer to W star. Okay. Okay, so now let's do the case where we choose like a smaller step size, let's just say just a complete constant, doesn't even depend on time, or a bigger step size, and see what happens. So this example here, yeah, in this picture, I chose eta t to not even depend on t at all, but just 1 over 10. So it's always 1 over 10. And this is what people call like a constant step size. This is actually used somewhat often in practice. And let's see what happens. So I'm just showing you visually. It means you start at W0, you calculate the derivative, the gradient, and then you take a step size of 1 over 10. The thing I want you to note is this is smaller than the optimal step size, which we calculated to be 1 over 2 plus e, which was the second derivative. So this is a smaller step size. And we do that again afterwards, which is once again still smaller than the, so this was at, yeah. So this guy here is equal to 1 over the second derivative at W0, which we calculated before. And then we also had that this thing was equal to 1 over the second derivative at W1, where W1 was 0. And W0 here was 1. And so all to point out that this 1 over 10 in both cases is smaller than the optimal step size. Okay? And so the effect is that you're taking steps that are smaller, and you are now farther away from the minimum than in the previous case, which you took the optimal step size. Yeah. I think W1 was 0. So, I mean, we can just go back up here. So, okay, in this picture, sorry, yeah, so maybe you're asking, is W1 here is close to 0.5? That's right. But what I'm saying is that, oh, okay, actually, this is a great point. So the optimal step size in this case, when you were here, I was using it in the previous case where you did a step of, and you got to W. But in this case, you would have used something like this. So maybe I just erased this. But at this point, the optimal step size would still be 1 over that second derivative thing, which would be 1 over the second derivative evaluated at something very close to 0.5. But which, once again, would be smaller, like 1 over 10 would be smaller than that quantity anyways. Okay, so the main important takeaway is this is a story that happens like all the time, which you should know, which is small step size slowly reaches W star. So it makes the rate at which you reach W star slower than the optimal rate. And it takes like these smaller steps. And then we could do the other extreme, which is, once again, what if we, like, we're setting the step size, but we don't really know what to set it to, right? Because we're not calculating second derivatives. So what if we set it to something too large? And the effect of this is the following, which here you set the step size to 1. And so 1 is quite a bit larger than 1, than 2 plus e. And the effect you have there is you start at W0, and now notice the W-axis is even larger than before. So I've expanded it to really emphasize this. So you started here, and before we took a step to like here, to 0. But now if your step size is 1, you take a giant step all the way to here. I mean, really, what you think about is you started here and you just moved this much as opposed to moving this much, which really just tells you that this distance from 0 to this is the difference between 1 and 1 plus 2 over e, 2 plus e, right? And then from here, you take another big step size, it's still 1, and you go all the way out here. And then if you were to do this again, you'd keep going and so on. And so you get the following result, which is if eta of t is large, then Wt can diverge. So you can see it's not even going to reach W star. So it can diverge from W star or oscillate. Yeah, or oscillate. So yeah, in this case, it really is diverging because it'll go here, and then it'll go here, and then it'll go somewhere farther and farther. And so obviously that causes problems. And so there's a lot of, yeah. So you get this kind of, I guess, maybe just to drive the point home, you get this like these kind of points that you should take away from this, which is like small step size is in some sense safe. So like, hopefully if it's small enough, you will get close to W star. However, it can take long. And the other case is where you have a large step size. If it's like large in the sense that it's kind of like correct, it's close to that second 1 over second derivative thing, it can get you to W star fast. And okay, one note is that notice that you could actually just like guess it perfectly immediately, in the sense that if you were here and you chose the correct step size, and by correct, it's like you could really pick a step size that gets you directly here in one step. Well, then your derivative is just going to be 0 here, and you're done. You're immediately finished. So like, yeah. So the second derivative thing is sort of, it's like, it gets you the same, it gives you a very fast convergence, but you could somehow, if you could calculate it, you could take the exact step size to get you directly to this point too. So yeah, if you have a really large step size, or if you have a large step size and you kind of guessed it right, you can get to W star very fast, as you can see. But if you guessed wrong and you made it too large, well, yeah, which we saw above, which is sometimes it can diverge or oscillate. Okay, so you kind of have these two trade-offs or issues that you run into, and we'll briefly talk about different step size settings a little bit later. But it's like a whole very active area of research. There's all sorts of different methods. There's kind of like standard ones that people now use, and they're just kind of defined in different machine learning packages where you can just call them and stuff like this. They're, yeah, they do all sorts of different calculations to kind of try to approximate this Hessian in an efficient way. But if you just want like a quick and dirty street fighting way to solve your problem, you just set it to like some constant. and you get what, I mean, you get some sort of behavior, and you can see, like, if things are diverging, then you're like, okay, that was too large. Let me change my step size to be smaller. And then you can just kind of iterate on your step size setting. And if you worked on any machine learning things or heard about this, people will call this like a hyperparameter setting. So like picking the step size is kind of important. So what you do is you don't know what it is. So you might try like 10 different step sizes, run your learner for all of them. We haven't really got to the learner thing, but like you're trying to optimize something, just run it for 10 different step sizes, all in parallel, and then look at which one actually got you closer to the minimum. And this will be called like a hyperparameter, which you tune by doing this process. And there's all sorts of other hyperparameters that we will sort of see some of them later on. And yeah, this is like just for terminology. Okay, so we did a bunch of this like single dimensional univariate gradient descent business. Now we move on to the multi-dimensional case. And once we kind of covered that, we can do the case where we're using the actual empirical risk, the estimate of our expected loss for machine learning, and see how that works. And it's fairly straightforward, as you can imagine. It's going to be like the same. Like you have this function that's going to be, that empirical risk is going to be your g of w. You take its gradient, which we already calculated because we had to do it for the linear regression thing before. And then we just take steps and iterate. And yeah. Okay, so let me just make it very clear how it works in this multivariate case. And yeah, someone asked online, can you explain how the step size is related to the atom optimizer? And so the atom optimizer is a specific way of setting your step size, which is based on like some calculations of various things that I don't remember. But it's basically an equation of how you set your step size at each step of when you're doing this optimization process. It's just some equation. It's not that long. It's like, it has like two or three things you calculate and plug them in, and yeah. But I just want to point, there's a bunch of different step size ways to set, and they call this the optimizers. Like there's an atom optimizers, there's like other ones, like there's momentum and things like this. So if you ever hear these things, it's just ways of like setting this step size. All right, multivariate case. What happens in the multivariate case? Well, first of all, the multivariate case is when you have a W vector that's coming from your domain, which we'll call RD, as we do for all this course. And it's multivariate, and I should probably write the title, which is multivariate gradient descent. And this is what we really, this is where you have gradients when things are multivariate. And so here you have your parameter is d-dimensional vector, and it will be multivariate. What that means is that d is greater than 1. Okay, that's what's happened. That's different from the last stuff. And you have your function, which is g of w. Right, that's your function. Maybe I write it as, it's a function from w, let's say, to r, or rd to r. It's what we've always been seeing. And yeah, now your objective, as we have seen before, is you want to calculate w star. W star is a vector. It looks like this. There is d dimensions, d components to the vector. And it's equal to, the definition of it is that it's the minimum w in RD of the function you care about minimizing. Okay, and so the gradient descent update rule, this is what people call it, will get you to this w star in an iterative way. Okay, so this is called the gradient descent update rule. We've seen it for one dimension, and it turns out to be exactly the same in the multidimensional case. The story's the same, you just replace the derivative, the first derivative, with the gradient. And so you get that, the w vector at time step t plus 1, this is your estimate of w star, is equal to your estimate at time step t minus your step size times the gradient of g, right? This was used to be the derivative, at w vector at t. So it looks exact, like, I mean, it's exactly the same when this is one-dimensional, because this is just g prime. And just to remind you, the gradient of g of w t is equal to the partial derivative of g at w1, which in general will be a function of w, the whole vector. And I'm just going to exclude this as I have been doing, up to the partial derivative of wd. And we've already done this calculation, if you remember, many times in the optimization thing when we set this to 0. We would take these partial derivatives, set them to 0, and we would get the minimizers. We would get these w star 1 up to w star d. Well, now we just iterate this update rule t times. The larger t is, the closer you're going to be getting, assuming your step size is chosen appropriately and you're not diverging. Okay. And the other thing to note is, once again, that for any finite number of steps, you can never be guaranteed that you're reaching the minimum, the minimizer. But you can be confident you're getting closer and closer if your step size is chosen kind of appropriately. Maybe other things to mention is, in theory world, there's all sorts of kind of conditions you need on the step size for this to hold, and on your function. You'll need things like that the step size has to itself be decaying as time is increasing. Because obviously, if your step size is constant, you're just going to keep jumping around unless you've perfectly hit the minimum. But if your step size is decaying at kind of the right rate, then it's okay. And so on. Okay, so these are kind of just theoretical properties that we don't really need to know about. And the next thing I have is an example, which we've kind of done before. Maybe I'll just say what the example is, and we'll work out the details. Oh, I have a picture. Why don't I just show you the picture, and then next time we'll write out the example. So here's my picture. I now have a two-dimensional function. This function, let me just write out what the function is. This is the function g of w, 1 w2, equal to w1 squared plus e to the w1. So this is like the function we've seen, but with a second dimension where you have w2 squared plus e of w2. And so we're going to see a couple examples of these multidimensional functions and what taking the gradient steps look like. And so in this picture, so this is our function. We have this, that's the like contour thing we have, or not the, like the multidimensional plane thing. And just what's going to happen is, if we make some guess like w0 over here, and then you do this gradient descent with an appropriate step size, then what will happen is you'll start here, and then you'll descend to the minimum, and then you'll take another step, and somewhere here is like the actual minimum. And we have different ways we can visualize this. We'll see that later. And you can do this for more complex functions as well. We'll talk about this next time, where you have this like complicated like kind of minimum somewhere here, and you just make a guess, and then you will slowly keep on descending to it. And so we can draw this for 2 dimensions. You can imagine what you're actually doing this in is much, much larger dimensions. And there we can't draw, but the same story holds. Okay, and so we'll pick up from here next time. And yeah, have a good weekend, everyone.